quick?
Good morning, everybody. My name's Eric Pratt. Like he said, I graduated in 2025, now working in Clarksville, Tennessee for Hankook Tires as a material design engineer.
And good morning, everyone. I'm Yazan Saran. I also graduated in 2025 with a bachelor's from Virginia Tech MSc. I am currently a ceramic engineer at Glengarry, working in Shoemakersville, Pennsylvania.
And unfortunately, our fourth group member, Sebastian Romanello, couldn't be with us here today, but I just want to let you all know that this project certainly could not have happened without his help. This work was conducted under the guidance of Dr. Brian Risch and Alyssa Kirscher of the Prysmian Group, as well as Dr. Gary Pickerel at Virginia Tech. Over the course of this project, we investigated a sustainable pathway for recycling cross-linked polyethylene, or XLPE, cable scrap by blending it with polypropylene to produce an injection-moldable plastic composite. To give you a quick roadmap for this talk, I'm going to be covering the motivation behind this work, as well as how we structured our research approach. Eric is then going to walk you through our results and how we arrived at our optimal blend formulation. And Yazan's going to close us out with our scale-up trial, reprocessing study, and overall conclusions. So with that, let's go ahead and get into it. So to frame the problem, it's worth briefly reviewing how cross-linked polyethylene is used in cable construction. Energy cables typically consist of a conductive copper core surrounded by an insulating jacket. XLPE is a really common material for this because as a cross-linked thermoset, it provides some excellent thermal and mechanical protection to the cable. That same cross-link structure, however, is what makes cross-linked polyethylene so difficult to recycle. While 80% of the materials in a typical cable, including the copper core and the thermoplastic components, can be recovered or reused, the covalent bonds formed during cross-linking prevent XLPE from being remelted using conventional thermoplastic recycling methods. Essentially, it doesn't melt, it just burns. So as a result, the XLPE waste is effectively locked out of the standard recycling stream, regardless of how well the rest of the cable can be recovered. This waste is generated from two primary sources, which are manufacturing over-extrusion and purging during normal production, as well as deconstruction of off-spec or rejected cable spools. Both of these streams currently end up in a landfill, and neither of them are a byproduct of any poor process control. They're just an inherent part of producing XLPE jacketed cable at scale. So this is exactly why we need to approach this problem as finding a new waste avenue for XLPE rather than trying to engineer it out of the production stream entirely. And shown on the right here is an example of what this cross-linked polyethylene waste looks like after it's been through the first processing step of granulation. And here's only one bin of the XLPE scrap, so the question is sort of how big of a problem is this really? So based on some figures provided by Prysmian, these waste streams generate approximately 2,000 tons of non-recyclable XLPE scrap annually. At a disposable cost of roughly $40 a ton, that translates to at least $80,000 in landfill costs every year for a single manufacturer. And that might not sound like much for the industrial scale, but this highlights how industrial waste is both materially and financially undesirable. At the time of this study, none of this material was being recycled by Prysmian, largely because there's been no established cost-effective pathway for reprocessing cross-linked thermoset waste at this scale. So that gap is sort of what motivated this study. So now we're going to move on to the experimental design and objectives of this study. Our work was guided by a few core sustainability objectives. First, we wanted to meaningfully reduce the volume of XLPE waste sent to the landfill. Second, we aimed to reduce the amount of virgin material that was required in downstream manufacturing, specifically virgin polypropylene, which is already used in cable spool production. And third, we wanted to establish a circular pathway that could plausibly be adopted at the industrial scale and not just in a lab setting. So taken all together, these goals pointed us towards identifying an optimal cross-linked polyethylene polypropylene composite blend that can serve as a genuine substitute for virgin material in real manufacturing processes, rather than just a formulation that performs well in the lab. So to translate these sustainability goals into an actionable research plan, we defined three specific technical objectives. First was to reduce the volume of landfilled XLPE by diverting it into a usable product stream. So to do this, we blended the recovered cross-linked polyethylene with polypropylene to produce a composite, and then we used that blended material to manufacture a functional component. And in this case, it's an injection molded cable spool. We deliberately chose cable spools as our target application rather than a more demanding use case like the cable jacketing itself, because spools have a lower mechanical performance threshold, which meant we could focus our early efforts on establishing feasibility before worrying about meeting some of the more stringent property requirements of any primary cable components. Since polypropylene is already used for spool manufacturing, partial substitution with recycled cross-linked polyethylene offered a direct drop-in opportunity to reduce both the waste and the virgin material demand without requiring any new manufacturing setups. So this means that we had the potential to implement our results right now to reduce waste rather than years down the line after exploring a bunch of different research avenues. So given the scope of the variables involved, we structured our project into two different phases. Phase 1 focused on establishing the relationship between the cross-linked polyethylene weight percent and particle size on the resulting mechanical and processing properties of the blend, with the goal of identifying a single optimal formulation. Phase 2 then took that optimal blend and scaled it up to an industrial trial, evaluating the manufacturing feasibility and the reprocessing behavior under production representative conditions. This two-phase structure let us reduce our design space, since first we could confirm our blend chemistry and the processing window at the lab scale, and then we would commit the material and manufacturing time towards a larger trial. Our final deliverable was a molded cable spool component produced from our recycled cross-linked polyethylene blend. So since both particle size and cross-linked polyethylene loading were expected to affect our blend's behavior, we built an experimental matrix of 4 different cross-linked polyethylene weight percents, which were 10, 20, 30, and 40, and we crossed that with 4 different particle size ranges, ranging from under 150 microns up to 600 microns. This gave us 16 distinct formulations to evaluate. Our workflow for each formulation followed 3 different manufacturing steps, which were sieving, compounding, and injection molding, and these were then followed by a battery of characterization techniques to assess the mechanical, thermal, and rheological performance, which Eric is going to detail shortly. I'm going to walk through each of our manufacturing steps in turn. So to start, we began with jet milled cross-linked polyethylene, which was sourced from an industrial partner, and this was supplied to us as a sub-millimeter powder with a pretty broad particle size distribution. Before outsourcing our milling to an industrial partner, we did explore a variety of milling techniques at Virginia Tech, which included a shredder or granulator, blade milling, and cryo milling. But unfortunately, none of these other techniques were worked well enough or were scalable enough to continue pursuing them past the lab phase of the project. So to isolate the 4 size fractions for our matrix, we sieved our jet milled material using a Rotap Model E mechanical shaker, and this had a stack of sieves corresponding to our target ranges, which were that less than 150, 150 to 300, 300 to 425, and 425 to 600 microns. It was surprisingly difficult to get a usable amount of cross-linked polyethylene in the less than 150 micron range, because at that size, the electrostatic forces, which are so prevalent in plastic, keep our powdery material clumped together, and they made sieving a challenge. This was important to note because any processing challenges that we encountered at the lab scale would likely become an even greater challenge at the industrial scale. This sieving step was also essential because without controlling our particle size directly, we wouldn't have been able to isolate its effect on the blend performance later on in the study. And it also reflects a practical reality of working with any reclaimed material, since unlike the virgin cross-linked polyethylene or any virgin materials, the jet milled cross-linked polyethylene arrived with a very broad and inconsistent size distribution. So we needed to get a repeatable starting point for the rest of our matrix. After isolating our particle size fractions, the next step was compounding those fractions with polypropylene. So our compounding was performed using a thermoscientific Minilab 3 microcompounder, which we operated at 190 degrees Celsius and 50 RPM with batch sizes of approximately 5 grams of material. This machine is just a benchtop twin screw compounding extruder, which is also used in industrial settings. The only major difference between the lab scale and industrial scale extruders is the temperature control along the screws and the cooling and control of the extruded material. So for this lab scale extruder, we only had 1 temperature set point, and our cooling setup was a simple conveyor belt that was placed next to the output of the extruder. Notably, we compounded our cross-linked polyethylene and our polypropylene blend without any compatibilizers, and we relied instead on the inherent chemical similarity between polyethylene and polypropylene to promote adequate interfacial compatibility between the two phases. And this was a deliberate simplification on our part. Compatibilizers are a common way to improve the adhesion between dissimilar polymers, but introducing one this early on would have added yet another variable to an already large experimental matrix, since we wanted to reduce the amount of new chemicals or processes required to implement our solution at scale. Our compounded material was extruded in these continuous spaghetti-like strands, which are shown on the right, and those strands were then pelletized in preparation for injection molding. So after pelletizing, we were able to mold a variety of test specimens using a mini-jet benchtop injection molding system, and we used a cylinder temperature of 200 degrees Celsius and a mold temperature of 120 degrees Celsius. There is a two-stage pressure profile, which was 500 bar for 15 seconds, followed by 150 bar for 10 seconds, to ensure complete mold filling and fairly consistent part quality. From each of our 16 formulations, we molded type 4 tensile dog bone specimens, as well as impact test discs. We did notice during our processing studies that the compositions which were approaching 40 weight% became much more difficult to injection mold, and we had some incomplete mold filling as well as bubbles occurring in the part. Once again, this was a lab scale observation that helped us inform our future scale-up trial. In total, this stage of the project produced over 200 individual dog bone specimens, along with hundreds of impact discs, which gave us a robust and statistically meaningful data set to carry into our characterization. With our full specimen matrix molded, we were ready to move into the mechanical, thermal, and rheological characterization. So that's where I'm going to hand things off to Eric, who's going to walk you through how we used that characterization data to down select from 16 formulations down to a single optimal blend.
Thank you, Will. So with the full test matrix built with every combination of particle size and weight% loading, the question becomes which of these formulations actually provides the best material for our application? To answer that, we leaned on three characterization methods: tensile testing, impact testing, and melt flow index, each one isolating a different failure mode or processing constraint. So starting with tensile testing, it's worth mentioning that we don't particularly care about the factors like ultimate tensile strength here, simply because a cable spool just doesn't see significant tensile loading in application. But tensile testing is still useful because of results like the Young's modulus and strain at failure. That data can give us some clear insight into how particle size is affecting the material's failure behavior. Impact testing is a much more critical factor for our use case. It's a pretty simple drop weight test. A specific mass is released from increasing heights onto our injection molded specimens until it fails. We followed a modified ASTM D4226 protocol, and we treated this as our most critical test that we ran because impact is the failure mode these spools are actually going to encounter in the field. These spools are loaded up on ships, on trains, on trucks, dropped off trucks, banged up, kicked around. They're going to take a lot of abuse. So if this material can't take that impact, then nothing else we're doing here really matters. Our third test was melt flow index, and this matters for a completely different reason: processability. So we need this material to be essentially a drop-in replacement for what Prysmian is currently running today. If the viscosity shifts too far from the standard, then it simply won't behave the same way on existing injection molding equipment. So melt flow index, if you're not familiar, is the inverse of viscosity. So as viscosity goes up, melt flow index will go down. And we ran this test per ASTM D1238 at 190 degrees C under a 2.16 kilogram load. So with that context, let's go through some of our actual results, starting with tensile testing. The tensile test data gave us a pretty clear visual story about particle size. Larger particles, shown here in the blue markers, as well as the upper image on the right, consistently failed at lower strain. The mechanism is pretty straightforward here. Under loading, the interfacial bonds between the particles and the matrix break, and a void nucleates right at that interface, and it grows until the material fails. Large particles create a small number of severe stress concentration defects. In the image on the right, you can see a large void where a particle used to be. However, small particles spread the same stress across many smaller sites instead, and you can see the difference in how they fail. The small particle samples show pronounced necking that's visible as these ring-shaped deformations at the fracture surface, which tells us we're looking at a significantly more ductile failure mode. Moving to impact testing. Again, this was a critical test for us because of our application. To test impact strength of our matrix, we tested various points along the matrix and then just filled in the middle until the story was told. The same particle size story shows up again in impact testing, but only up to a point. Our baseline, Prysmian's current recycled polypropylene, came in at 5.4 joules impact strength. For our composite, once we introduced our particles at the 10% loading, we saw a significant drop off with increasing particle size. So at our smallest particle size of 150 microns, we were still slightly above the baseline. But once we got up above 300 microns, we fell down to 4.9 joules. However, once we increased our loading up to 20% and above, that difference caused by particle size started to disappear. And once we were above 20%, between 20 and 40 within our particle size range, there wasn't really any statistically significant difference caused by particle size or increased loading. So what we get here is essentially a threshold effect. Below 10%, there's a significant effect of the particle size, and above it, there is no significant difference. And we can see that mechanism here in our tested samples. On the right, at 30 weight% with our largest particle size, the fracture surface shows some discoloration in a band around the edge. This is clear evidence of the interfacial delamination concentrated in one region. At our smallest particle size, we instead see extensive microcracking spread across the entire surface. That's a direct consequence of surface area. The smaller particles give us far more particle matrix interface, which means far more potential crack initiation sites. And rather than concentrating failure at one large defect, the dense network of microcracks lets the surrounding matrix flex and absorb energy across many small sites at once. Finally, melt flow index. Again, this is simply a measurement of processability. Relative to a 100% polypropylene baseline of 2.29 grams per 10 minutes, our 20 weight% loading samples dropped the melt flow index by 18%. And that's essentially our processability ceiling, since anything much beyond 20% drop risks becoming unworkable on existing equipment. However, once we push to 40 weight%, that drop gets significantly more dramatic, another 60% on top of that, for a cumulative decrease of nearly 80% off the baseline. And just like impact, particle size itself makes no meaningful difference at either loading level. So this is more of an issue of weight% than particle size. So to put all three tests together, the decision becomes fairly clean. Melt flow index turns out to be our more restrictive of our two critical constraints, capping loading at 20 weight%. Particle size, meanwhile, only meaningfully affects tensile behavior, which isn't a governing property for this application. And its influence on impact and processability starts to disappear well below the 20% ceiling. So our optimal formulation that we chose was 20 weight% XLPE with no restriction on particle size below 600 microns. This means that we don't have to do nearly as much fine particle separation when we're scaling this up to a manufacturing scale, because that type of sieving, as Will discussed earlier, takes a lot of time, energy, cost. It's just not really a scalable option. So that closes out phase one. Phase two, we're moving on to our scale-up trial, testing the properties of our final blend, and then we'll answer a question about recyclability. And Yazan is going to take it from here.
Thank you, Eric. So to kick off our scale-up trial, the first thing we needed to do was to sieve out and blend approximately 50 pounds of our optimal blend that we could then ship to our partner Prysmian for large-scale industrial compounding. So unfortunately, the largest obstacle that we faced during our entire project did end up occurring in this critical stage of phase two, which is we simply did not have enough crosslinked polyethylene to actually reach the 20 weight% threshold with a bulk sample like this. We also, at this point, we were all out of time. We could not wait to receive more cross-linked polyethylene, so we made the decision to move forward with a 16 weight percent cross-linked polyethylene and polypropylene blend for our bulk sample. Thankfully, we found that this served our purposes just fine. So after a week-long process of sieving out and mixing our bulk sample, we sent it out to our partner for industrial scale twin screw extrusion, compounding, and pelletization. The compounding trials were performed under the same parameters that we use when we compounded our blends in-house at our Holden labs and were a large success, meaning that we could move forward in delivering on our molded spools. We received a small portion of the pelletized material back for further characterization and testing, while the rest of the 50-pound bulk sample was sent to our injection molding partner, Vandor, and our molding trials were very successful. On your left, you'll see a short video showing the industrial molding process performed in Vandor in our presence. And on your right, you can see our team surrounded by a whole lot of molded flanges made from our blend, 20 of them, in fact. And these flanges were later assembled together and made into fully functional spools. This injection molding trial highlighted the success our team had in delivering on one of the primary goals we set out to achieve during phase 2 and over the length of this project as a whole, which is our molded spools. However, we weren't done quite yet, as we still needed to both characterize and test our optimal blend and conduct our reprocessing study. The first test we ran on our new blend was melt flow index, which, as previously mentioned, is crucial in helping us determine the processability of our blend. Our test showed that our blend had a melt flow index value of approximately 1.8 grams per 10 minutes, which is a 20% drop from the baseline control polypropylene samples, which tested at 2.29 grams per 10 minutes. But it was still well within the range of values that we deemed acceptable and processable. After that, we performed the same drop impact test as before on our new blend, and we found a 38% increase in impact strength, a result that was both exciting and anticipated with an impact strength of almost 9 joules, well above the 5.4 value of our baseline polypropylene. We also performed tensile testing on our optimal blend, and we did find a significant drop in both tensile strength and the elastic modulus from our control polypropylene samples. This test, while not integral to the success of this application, still provided good information for us and actually tied very well into our reprocessability study, which Eric will now go into detail on.
Thank you. So we didn't want to just stop there with a successfully molded spool, a optimal blend. We also wanted to make sure that our material was also going to be recyclable. It would be a shame to replace Prysmian's current recycled material that they use for cable spools with one that can only be used once or twice before significant degradation occurs. To answer this question, we conducted a reprocessing study across 10 cycles, R0 through R10. In this study, we molded tensile specimens, tested them mechanically, rheologically, and thermally, then remilled those samples, molded new samples with that, and then tested again for a total of 10 cycles. We used 2 tests to evaluate the degradation of our material: zero shear viscosity and oxidative induction time. To determine zero shear viscosity, we conducted a frequency sweep on a hybrid rheometer. Excuse me, some technical difficulties. The frequency range we used was 0.01 radians per second to 0.2 radians per second. The zero shear plateau was identified and 5-point values were averaged across the plateau, giving a theoretical zero shear viscosity. With those viscosity values, we could compare the molecular weight. Now, typically, you would need a material constant to determine molecular weight from viscosity. But since we were looking at a change rather than an absolute value, we can negate the material constant and report a change in molecular weight. To do this, we use the power law with some equations shown here on the slide. And moving on to oxidative induction time, this was conducted on a TA DSC machine. The process here is to load a sample in an open crucible so that it is in contact with air. The DSC measures the heat flow in a material under various heating and cooling conditions, and our test followed ASTM D3895-07. And essentially, the sample is heated at a rate of 10 kelvins per minute until it stabilizes under an inert gas, in this case nitrogen. After stabilizing, the inert nitrogen gas is switched to oxygen. This marks the start of oxidation. The test continues until an exothermic reaction is visible. This exothermic lift marks the onset of oxidation, and the oxidative induction time is the time of the start of the oxygen to the onset of oxidation. So for our results of this study, between R0 and R10, the zero shear viscosity dropped by roughly 29%, which translates via the power law relationship to about a 9% reduction in molecular weight. And yet the tensile properties stayed statistically unchanged across all 10 cycles. There appeared to be some drop in the Young's modulus, but based on our test results, we couldn't find any statistical significance to this. This tells us that the modest molecular weight loss isn't yet translating into mechanical performance problems. The oxidative induction time, sorry, I skipped through these. The oxidative induction time is our proxy for long-term environmental stability. And even at R10, our 10th recycling process, the oxidative induction time came in at 17 minutes. And while this is a 54% drop from the original material, it's still comfortably within an acceptable range for this application. For some context, the standard oxidative induction time requirement for cable jacketing material is 20 minutes. So nearly reaching the standard for the material itself for our packaging material seemed perfectly fine to us. So after 10 full reprocessing cycles, the material is still mechanically sound and still oxidatively stable. And that's really the whole point of this project. We're not just trying to divert XLPE waste once, but providing a blend that can be circular and exist in the recycling stream for some time without losing properties that make it usable in the first place.
So to conclude, our design project mapped out into 2 phases across approximately 3 semesters of work and testing. Phase 1 constituted characterizing our baseline material and characterizing our 16 potential blends, using all that mechanical and rheological data gathered to then select an optimal blend. Eric, if you could. Doing so, we concluded that particle size was a non-limiting factor, while the composition or weight percent of the cross-linked polyethylene in the polymer matrix was the governing factor when it came to the processability of our material. Therefore, we were able to move forward with a selection of 20 weight percent cross-linked polyethylene at all particle sizes under 600 microns. Phase 2 included our scale-up trial, where we received and blended a 50-pound bulk sample of 16 weight percent cross-linked polyethylene and polypropylene, shipped that bulk sample to Prysmian for them to perform their industrial scale compounding and pelletization trials, and then shipped our pelletized blend to our injection molding partner, Vandor, delivering on our primary deliverable of a functional molded spool. We also then proceeded to test our optimal blend in-house and performed our reprocessing study. And we found that our blend had greatly improved impact strength from the material currently in use, had a high level of recyclability, and more importantly, we found that our project plan and process is in fact industrially scalable with our successful molding trial of multiple cable spools. For future work, we had hoped to take a closer look at environmental stress crack resistance, explore the addition of other additives and surface treatments into the polymer matrix to increase functionality, reduce the degree of cross-linking through heat and shear forces, allowing for an even higher degree of recyclability to the material, and to further expand on our reprocessing study. One thing to note is that there is currently a new rendition of the Prysmian team at Virginia Tech MSc, working closely with Dr. Risch and Dr. Pickrell as we did, and they're actually following up on many of these topics with their own detailed research project. We thank them for choosing to expand on what we believe to be a spectacular sustainability initiative, and we wish them all the best. We would like to acknowledge Dr. Brian Risch and Alyssa Kirscher from the Prismine Group and Dr. Gary Pickrell from Virginia Tech MSc, our technical advisors for this project who were with us every step of the way. Robbie Davis and the team at Vandor who helped make Phase 2 possible, Professor Christine Burgoyne and Dr. Thomas Daly from the Virginia Tech MSc Department, Samuel Libestock, Glenn Spearing, the 2023-2024 Prismine team for all their help, and the 2026-2027 Prismian team. We thank you all for attending this webinar with us today and for your time, and we are now open to hearing your questions.
Yasan, thank you. And you nailed it when you implied that this was such an excellent university and industry collaboration. I think this is obviously a very important component of our business in the cable and connectivity industry, but elsewhere as well. And you certainly picked a difficult material. Any cross-link material is difficult to reincorporate into the supply chain. So we applaud you for that. We thank you and Eric and William, of course, for presenting today. I do want to apologize again to those of you who didn't join the presentation until a little late because we had a Microsoft Teams glitch. They infamously update things without telling people. So we apologize for that, but I do want to mention a couple things that I mentioned in our introduction, and that is that this webinar will be archived from our website. You can reach it also on our YouTube channel for you to share with your colleagues and friends in the future. Also, not only was this presentation well recognized at our Pittsburgh conference last October, but it was also received the third place national award from ASM, which is the Material Education Foundation, the undergraduate senior design competition. So this has been well recognized as an important accomplishment. And again, the whole team that Yasan mentioned should get exceptional recognition for. So we thank you. If you have any questions that you haven't yet posed in the chat, please do so. There are a few coming in. So to the team, what was the particle size distribution of the co-compounded polypropylene?
Yeah, I can answer this one. So it was the same particle size that we sieved out. So we just took the that XLPE powder directly from our sieve stack, and then we fed that into the top of our compounding extruder. And when we compounded, we let it run for around 10 to 15 minutes to fully combine all of our polypropylene with our sort of powderized XLPE material. So it's just the same exact powder that came out of our sieve stack.
Great. And what is the performance when all particle sizes are mixed together and not sieved or sieved?
I'm going to let Eric go ahead and answer that one.
Yeah, so if I'm understanding correctly, he's asking if there's a difference in the mechanical performance of the material with our entire range versus our smaller matrix ranges. Is that the question?
Yes.
Let's see. I believe we have the tensile results for that. So the yield strength coming around 20.
Yeah, I don't know where the graph went.
Yes, almost no change in like the ultimate tensile strength. The impact strength was actually improved over all of our blends. So the result we got from the the wider range of particle sizes outperformed in impact testing and no change in tensile ultimate strength.
Very, very good. Do you know, or do you do any LCA or LCI for the GHG emissions differences?
We didn't do an explicit like LCA study on this. However, since our solution is displacing virgin polypropylene and reducing waste, if for anyone familiar with LCA, you'll find that a lot of times the greenhouse gas emissions come from the production side of things. So by displacing any virgin material, we usually have a very large offset in the greenhouse gas emissions. So I would assume that our solution has an overall reduction since we're reducing that virgin polypropylene, but I can't give you any explicit numbers since we didn't focus on that for this study.
And
Great.
to do the true analysis, you'd also have to look into some of the logistics, shipping and everything. But if all of our processing was done locally, so we'd also reduce some shipping as well.
Yep. Thank you, Brian. That's correct. It's complex to do those measurements, but anyway, that's another topic for another.
It's another design project.
There you go. Yeah. Could this approach be used for cross-linked polyethylene received from, say, field installed XLPE insulated cables at the end of their working life?
Yazan, do you want to take this one?
Yeah. Yes, that was kind of the question we aimed to answer with our reprocessing study. And we only kind of recycled and reprocessed things 10 times. But from all the further research that we did, all those papers that we read and studied, we are very confident that you can go well further beyond 10 cycles. A lot of studies not including a durable material like XLPE and more focused on stuff like PVC and nylon concluded that you could recycle it with minimal mechanical property drop-offs up until around the 20 cycle mark. So we feel pretty confident that cable jackets nearing the end of their life would still provide overall benefit to the impact strength, and while not severely damaging the processing and the melt flow index of a blend like this in this application.
To add to that, in this case, the XLP is more of a functional filler than a integral material property that we're using. So it's not like in a lot of cases, a blend, you'll kind of be averaging the material properties of the two components. But whereas XLP in our case is more of a functional filler, it doesn't have a huge effect depending on the condition of the XLP itself.
Right. Again, general comment, this is a great project. And again, we applaud you all for doing this on our collective behalf. Would you consider perhaps other thermoplastic materials such as PVDF or PVC?
Yeah, so actually I got to double check with Dr. Risch here, but I believe the next senior design project is working on compounding XLPE with a different polymer. Is that correct?
Yeah, polyethylene. And
Okay,
we're going to dive into, and I know you've been mentoring the team. Thanks for your continued assistance. Shout out for you. And so basically we're going to follow up on some of the work. We're going to look at stress cracking behavior, which might have a different relationship to particle size. And we're focusing on, a polyethylene matrix material, as that is more commonly used in the wire and cable industry. There's also a lot of PVC scrap that we're dealing with. So there's multiple aspects of this project, as well as, things like the LCA analysis. So it's a, continued work, room for continued number of teams to work on it moving forward, and teams within Prysmian have continued to work on this problem. It's a global problem. It's with a company the size of Prysmian, it's a big impact.
Yeah, and as we all know, every cable design, whether copper or optical fiber, contains multiple matrices of materials. So it is complex, and contamination and other issues have to be sorted out. How was the cross-linked polyethylene processed before it arrived at your lab? Was there any levels of metal contaminations?
Yeah, so we have a supplemental slide on this, Eric, for the jet milling. So we had an industrial partner jet mill our cross-linked polyethylene, and jet milling is essentially you take the material and you throw it into a cyclone, and it hits itself until the particles become small enough to make it out the top. So there you see sort of the diagram of the jet milling machine. And one of the beautiful parts of jet milling is there's no additional blades or milling media or like any other large contaminants, since the material is just milling against itself. So we really reduce the amount of like milling contamination in our material through jet milling, and it's a really scalable process. So we can jet mill a large amount of XLPE as long as you have enough compressed air going into the machine.
Right.
We
When was the 190 degrees C temperature used when you molded the flanges? And the question is, were there any concerns with running hotter than 190 C? If your R10 heat history was all at 190 C, there's a concern that the real life processing parameters might enact more damage on the materials.
Eric, do you want to talk a little bit about the temperature for the reprocessing?
Yeah, so if I'm correct, the question is
the threshold of 190 C, is that if you go hotter, is that going to cause any more damage?
I would assume that it would, because the heat history is just going to add up a lot quicker. You're probably going to have more drop in molecular weight from that higher processing conditions. So could definitely affect the mechanical properties, likely the oxidative induction time as well.
Yeah, and right. To add on to that, I'll say that 190 was selected for our benchtop twin screw extruder because polypropylene generally melts around like 160 to 180 or 160 to 170 C. And in general, twin screw extrusion processing of polypropylene is in the 180 to 230 degrees range. So we were keeping to the low end of that because we wanted to reduce any potential damage to the polypropylene. And the reason for that is the benchtop extruder, it essentially cycles the material back to the start, and it runs it in a loop for however long you let it run for until it's fully compounded, and you can extrude it out the side. Generally, for the industrial scale, it's a linear process. So you're adding your material in at the beginning, and then it becomes fully compounded by the time it reaches the end of the screws. But since we knew that our material was going to be in contact with the 190 C for longer, we wanted to try and reduce some of that thermal history. And it also made it faster to cool our plastic as it came out the side of the extruder, which means we could get into the injection molder a little quicker. And each of these processes, we could mold about we could compound about 5 grams of material at a time. A tensile dog bone takes about 4.5 grams of material. And so it's 10 to 15 minutes to compound, 5 to 10 minutes to cool it, another 5 minutes to get it into the injection molder and heat it up, and then, a minute or two to get that out. So you're looking at roughly 30 minutes for a dog bone. And we molded over 200 of these. So any time that we could cut out, letting our material cool down once it was out of the extruder was super helpful. I believe I was pulling up the parameters here for the scale up trial. When they were running it on their twin screw extruder, they were running 225 degrees Celsius at 400 RPM. And that worked out pretty well for theirs. So there's not a significant problem running the polypropylene hotter. And even in our reprocessing study, you saw that it had a little bit of a drop after 10 reprocessings, But generally, if you're using this in a cable spool application, how many times is it going to get ground up and reprocessed? As long as it can survive the first 2 or 3, you've already extended your service life dramatically.
Very good. Thanks for that. That's a very good point, and does show that there is a range of temperatures that still could be used. Time for just 2 more questions here. The question was, I guess it would not be easy to grind cross-linked polyethylene to a fine particle. So with that, do you think it will be applicable in a commercial scale at an acceptable cost?
Yeah, so like we said about the jet milling, I can attest it is not easy to grind XLPE to a fine particle size. I think Yazan and Eric could definitely chime in on this. We spent a lot of time trying to find a way to get that particle size down while we were at Virginia Tech. The best method that we had before jet milling was essentially a spice grinder. It was like a high power blade grinder, and even that it took like Eric, do you remember how long that thing was in that grinder for?
Way too long. Long enough for it to overheat, and we'd have to turn it off, let it cool down, and then start it up again.
Yeah, so very difficult to get that down. The most effective milling that we found was actually the cryo milling. It's essentially a shaker mill with a metal impeller in the center, and the whole thing gets dunked in liquid nitrogen. And that was fantastic for getting really fine XLPE. But obviously, cryo milling is not exactly scalable. So the jet milling was a fantastic scalable process to get pretty repeatably fine particles that we could then sieve out and use a lower, cutoff limit for the particle size.
Great. One last question. Besides the injected cable spool that you generated, what other types of deliverables or products were considered for the use of recycled cross-linked polyethylene?
Yazan, you want to take this one?
Yeah, sure. So within the scope of this project, we kind of honed in on cable spool just because they're necessary for a cable company to produce, obviously. So, to keep things confined within Prysmian and kind of have immediate impact on their production, on the production level. But it is, I do not imagine it being ever a problem to integrate a cross-linked polyethylene into any polymer matrix with another polymer to produce all sorts of anything you can mold. You can use it as long as you have run your tests, you have materials that are either similar enough, or you can add a different additive that can kind of as a compatibilizer. You can definitely repeat this process on any number of polymer molded products, I imagine. But Dr. Rich would probably be a bit more knowledgeable about that. We didn't really explore a lot out of the scope of this project. Unfortunately, we just didn't have enough time.
Well, listen, you picked a great one for our cable industry anyway, as far as using the materials in spools. That's a very important component of our deliverables in our industry. So anywhere where we can find usable applications is good. But listen, what a great start. And this, again, will be useful and inspiring to other collaborations between industry and those folks trying to recycle plastics, and also academia to help us understand how to do that and also the potential impacts. But anyway, thank you to all 3 of you, Eric and William and Yazan, and to Brian, of course, to bring this to us and to give us some thought on how to move forward. And we look forward to the next projects that you have working at Virginia Tech, and we hope that you'll consider IWCS to present those in the future. Again, I want the audience to recognize the email addresses if you want to reach out to any of the presenters today. We certainly thank your participation in today's webinar. And again, if you want to share this with your colleagues, it will be available from our website and on our YouTube channel here in a few days. Our next webinar series will take place, typically the technical paper webinars are on the third Friday of each month. So therefore the next one will be on Friday, August 21st at 10:30 a.m. Eastern USA. We recognize that many of you are from all parts of the world. So again, good morning, good afternoon, good evening. And again, for those of you who are late into the evening, we thank you for your time and your engagement today. Before we conclude, I do want to recognize our sponsors, our premier partner sponsors, who without their generous contributions and technical contributions, we would not be able to bring this important information to you. So again, we want to thank all of our global partners who participate with IWCS, and thanks for their continued involvement and support. And I do want to remind you that coming up fast is our 75th anniversary IWCS Cable and Connectivity Industry Forum. It's taking place at the wonderful Gaylord Palms Resort and Convention Center in Orlando, Florida. We invite all of you to participate. The preliminary program has just been posted on our website, iwcs.org, and you'll be receiving a email blast with links to that. So it's all coming together very rapidly. We still have a few things to wrap up and provide information on our executive session and plenary speakers, and of course our celebration. We're going to have a fun Monday evening, a Cirque Royale. So we're going to generate a small-scale circus at Gaylord Palms on the Monday evening. So we want to celebrate the 75 years of contributing technology innovation to our industry. So again, we want to thank you all for participating today and look forward to having you at our future webinars, but also if you can, bring your family, come join us in Orlando in November. So with that, have a great rest of your day and enjoy another fun summer weekend. All the very best. Take care.
Awesome. Thank you so much.
Yeah, thank you for having us.
Thank you. Take care.